Okay, take it away, Maria.
Hi, everybody. My name is Maria Trnkova. I'm at the University of California in Davis. And today I would like to share my work that was done in collaboration with Joel Haas, also here at UC Davis. So we'll talk about approximating embedded surfaces by triangular meshes. And so I think that this talk suits better than any other of my research projects because I saw a lot of biologists and medical people here. So hopefully it will be understandable and you'll have some questions. So from biology, for example, we know that we want to see a surface. We know something about a surface or an object. We want to see it, but we don't have this opportunity. For example, we can do MRI or CT scans. We have this data and we want to see organs that are inside. We want to visualize them. Or maybe we want to visualize some objects, characters in movies, in animations. And so how is it done? So actually we are making a surface that is called a mesh. It's a collection of triangles. And then we want to put some graphics. So we want to color it and it looks nice. So in computer, it's stored like this, a bunch of triangles sitting next to each other. And then we put a raster graphic on it based on some information, and we can see objects like this, nice and smooth surfaces. Why it's important? Well, we want to see some damages, some deformations, some abnormalities. That's the reason why we want to visualize them before we'll do surgery. And so using computer graphics language, it's called a mesh. And there are different types of meshes. We consider mesh that are made out of triangles because that's the basic object. And you have a bunny here. This is a standard classical, like a toy model. And then we want to make a triangulation. And this bunny is stored like a collection of triangles that we can see later. So, okay, triangles are nice, but triangles are different. And we can take the same surface and we can triangulate it differently. And now you can see 4 different meshes of the same object. And in the second row, we zoomed in to see differences. And so how do you think, which mesh here is the best? So the answer will be, depends what's your goal. What do you want, what qualities of your mesh you want to get? If you want to have as best approximation as possible, maybe it's this one. But if you look at the triangles here, some of them are very skinny triangles, and for computations, they may be very difficult to use them. If you look on the right side, then you have some like points, and this is not very smooth, but on the other side, it's very well describes high features, like where you have high curvatures. There are lots of tiny triangles, but you can see that this ear is very well described, looks very natural. And so what is our idea? So we have a surface. It's described by as an equation maybe in the space, and we want to cover it with triangles that have nice shape. So nice shape for us means triangle is very close to equilateral, as close as possible. Why is it important? So if we have triangles that are very skinny, like needle shaped, it's hard to do some testing. So if you have a triangulation of an airplane and you want to do testing for crashes, for example, you'll do some simulations and you have to solve differential equations. And you just cannot, because here you'll get huge errors and the result won't be accurate. So in order to have accurate results, you want to avoid this shape of triangles. And so we developed an algorithm. We called it grad normal algorithm. So I will not talk the details of the algorithm, but I'll tell you what it does. So for example, we'll take this toy model, the bunny model, and it has a lot of triangles. So 58,000 vertices. And some angles of triangle are less than 1 degree. So it's 0.5 degrees, so very, very skinny triangles. So when we run our algorithm on this poorly triangulated mesh, first of all, we were able to have less number of vertices. So it's not double, but significantly less number of vertices that we got in this mesh. And what is important, the smallest angle among all triangles is now 10 degrees. So this is a huge difference. And so for computing differential equations, it's perfect. So, and we noticed that, well, first of all, this needle triangles you probably won't see, but we found some places where we can demonstrate. So it's behind the ears of the bunny where this curving happens a lot. So here we had some very skinny triangles. So maybe I'll zoom it once again.
Also, Maria, you have about less than a minute to go.
Okay, yeah. So we have these skinny triangles, and after we retriangulated, now you can see that it's perfect. So these are thick triangles. So the idea that we used was not super new, but it was very similar to Martian cubes. If you've ever heard about Martian cubes, it's one of the famous algorithms. So it's based on cubulating the whole space and then see how surface intersect these cubes. So our idea was a little bit different. So we used tetrahedra to divide the whole space. And then, so these are types of tetrahedra that we used. And then we saw how our surface cut this tetrahedra. So here is a surface in blue, and then we replaced it by some pattern by this red triangle, and we projected them back. And so using this idea, we were able to improve the angles. So maybe I'll skip this.
So yeah, can you finish up now, because you're over the 5 minutes.
Okay, so yeah, so here is the graph that we took original bunny, and when we retriangulated, so we can see how angle distribution changed. So thank you very much.
Great, thanks. Does anybody have any questions? Well, I was going to say, you had mentioned this is for medicinal work. So how is this computational work then translated for medicine?
So you get a visualization of the object that was scanned, and then you want to see, you want to measure volume, you want to see the surface, you want to see fractions, if a bone is whole or if there is a fracture in that bone. So yeah, it's that's how it's used.
Okay, great. Yeah, sounds very interesting. Thank you.
Okay, thank you.